Hello, everyone. Thanks for joining. 5 things you need to know about edge computing. I would like to start off with introducing both Akim and myself. Akim Krumbach is Solutions Architect at CenturyLink, working together with the cloud team. My name is Mark Schultinger, and I'm Director of Content Solution Distribution. Been with the company for 1 year, responsible for CDN Edge products. Today, we're going to talk about what you need to know about Edge. I have a short agenda. The whole presentation will take approximately 20 minutes. First, we're going to start off with edge computing. What is it? Where is it coming from? Then we'll move over to IT, cloud, and edge compute. Third, go into what is edge and the CDN. And 4, talk you through the modular design. I'll hand over the floor to my colleague Akim now.
Thanks, Mark.
Akim, there you go.
Often edge computing is seen from the perspective of 5G and Internet of Things. While these need edge computing can be done as well without them. Let's take a step back and look at edge computing rather from a general and architectural point of view and how the location of computing evolved. The word edge in edge computing describes its location in the network. Hence, let's start with a look at the architecture of the network. Starting at the border of the network, users, private users or enterprises, are connected to the access tier. This tier is characterized by the multitude of technologies like Ethernet, Wi-Fi, DSL, FTTX, or mobile networks like 4G and 5G, or even older legacy technologies like SDH and SONET. The traffic of all these users, and this way all these technologies, is collected in the aggregation layer and transported to the central core network. This is where the big bandwidths are. What is the edge? The edge is historically the demarcation between the access and the aggregation layers, where the different traffic streams of users were combined. It is as well the location where for the first time this network traffic is analyzed, categorized and classified, and its further handling and routing is determined. Hence the naming edge of the network. In case of MPLS network, this function is performed by the so-called provider edge or PE router. The main competency is a classic definition of traffic types. In the last 10 to 15 years, there has been a constant tendency to centralize computing. Local server rooms have been closed and respective workloads have been moved to central data centers to achieve economies of scale. Often only workloads like print servers, software distribution servers, and so on remained on site. Consequently, enterprises had all their workloads in one global data center or maybe a few continental data centers. For example, one for Europe, one for America, one for APAC. Why did this happen? Enterprise did this for several reasons. First, it mirrored the organizational and governance evolution. IT was not anymore a local matter. It became centralized, globally shared business units. Second, it is hard to provide a high level of service across a distributed infrastructure that often was rather heterogeneous. Centralization reduced the complexity and standardized processes and maintenance. Services are easier to implement and manage inside one data center. Third, and perhaps most important, it was cheaper, as it provided significant economies of scale and scope. And the emergence of hyperscale cloud providers like AWS, Azure, Google did not change this architecture significantly. While there were several regions to choose from in a certain geography, enterprises still selected, in most cases, one cloud region for all their workloads. As the dominant application model was client-server, nearly all traffic was routed from the user across the network tiers to the central data center, or respectively cloud region, was processed there, and the reply was routed back to the user. Peer-to-peer traffic, it's rather the exemption. There are 2 disadvantages with this model. First, latencies, and second, bandwidths in the center. The latency between users and the central data center can be substantial. especially if there is just one data center globally. This impacted the user experience as web applications took longer to load, virtual desktops longer to respond, and so on. But it still worked. Functionality was not impacted. Similar with the increase of bandwidth in the center of the network. It increased significantly, but the technology was still able to cope with it. And if there were problems or challenges, there was a remedy, at least for web applications, the Content Delivery Network, CDN, a distributed storage and caching system. Lots of CDN nodes were installed at edge locations globally. When a user requested a piece of content from a central server, the request was routed to the next CDN node. If the content was cached there, the CDN node replied directly to the user, reducing latency and network traffic at the core. And only if the content was not available in this CDN node, only then the request was sent to the central server. The reply of the central server was routed back via the CDN node to ensure that it would be able to reply back directly to the user the next time someone needed this information. But this does not work anymore today. The latency does impact functionality, and the core is challenged to cope with all this bandwidth required. One reason for this is that users are increasingly not human, but becoming more and more machines. Just imagine a self-driving car is filming its environment, including a red light. If it sends a video stream to a central site for processing, it will be already in the middle of the crossing in an accident before receiving the reply with the command to brake from the center of the network. This is the best example I can think of, even if I hope that such tasks will not be formed at the edge, but rather directly inside the car. Similarly, have a look at the growing number of CCTV cameras installed everywhere. If all of these cameras send their HD video streams to a central site for processing, for example, image analysis, if a certain person is visible in the video, the core of the network would be quickly overwhelmed by all these HD streams. Hence, there is now the growing need to perform compute activities already at the edge, closer to the user, and now without using huge amounts of bandwidth in the core network. In the end, closer to the place where the digital interaction is happening. Just to avoid any misunderstanding, the majority of computing will remain in the central data centers and hyperscale cloud provider regions. Edge computing will be required only for certain latency-sensitive or high-bandwidth applications or services. As with the question public cloud versus private cloud, the question where and when to use edge computing is about developing the individual right compute mix for an enterprise. Generally, there are two forms of edge computing, full computing and pre-computing. In case of full computing, the user sends his request across the network to the next edge node where it is processed. The reply is directly sent back to the user with a minimum latency. This would be the solution for the self-driving car approaching the red light, if the processing is not performed already inside the car. In case of pre-computing, the user's request is sent to the next edge node, pre-processed there, and only the results are transmitted to the center. For example, the different CCTV video streams are analyzed by machine learning or artificial intelligence algorithms at the edge, and only the information about the recognized things or persons is sent to the center. This results in a significant decrease in required bandwidth in the core network. How can IT service providers support enterprises in deploying and managing edge computing solutions? Traditionally, IT service providers applied the same centralized architecture. For them, the financial benefits of centralizing customers' computing environments in a few large-scale data centers were as well significant. Shared infrastructure, shared processes, shared tools, shared platforms enabled them to achieve economies of scale and scope and to provide this way their customers with the expected cost benefits. Thus, they had limited numbers of data centers globally. Typically, at least one or two on every continent. more than these typically only on their own home continent. For example, European providers have often DCs in Germany, in the UK, France, and so on, while US providers have several data centers locations across the US. Similarly, they have their centralized operations locations, sometimes applying a follow-the-sun model with teams working from EMEA, from APEC, and from the Americas. The model of cloud hyperscalers is nearly identical, even if the number of regions and zones is significantly larger than the number of data centers of service provider. Several regions across the US, some regions in Europe and APEC, and maybe a few regions in Africa, South America, and India. This architecture changes with the arrival of edge computing. These data centers will remain and will probably continue to grow, but service providers are extending their operational model in a way that is nearly revolutionary for them. Now, both IT service providers and cloud hyperscalers extend their deployment model to new third-party data centers, smaller cloud locations, and even installing equipment on customers' premises, something that was anathema only a few years ago. This is supported by compliance requirements that make the centralized computing model less viable for all applications of an enterprise. Especially in Europe and APEC, regions that consist of a multitude of countries, each with its own compliance requirements. For example, IT service providers that have data centers, for example, in the UK and Germany, face a challenge to provide IT service to Swiss financial enterprises, as financial must not leave Switzerland due to its data compliance requirements. Let's look at the details of these new scenarios. Third-party data centers mean that service providers deploy and operate infrastructure in data centers where they have no existing infrastructure, no existing shared network, no shared storage and backup systems, no management systems like jump servers, firewalls, DNS, DHCP, and so on. This missing infrastructure made individual solutions in such data centers in the past exorbitantly and in most cases prohibitively expensive. But today, installations in any data centers without any pre-existing infrastructure of the IT service provider to fulfill edge computing requirements have become feasible financially due to the arrival of two technologies in the last years. Hyperconverged infrastructure, where compute, storage, and network resources are software-defined and combined in one piece of hardware, and network function virtualization, where network functions are implemented as virtual machines and not as separate hardware appliances anymore. This way, the required infrastructure, both the resources to be used by the customer and the service provider's administration tools, can be collapsed in a few pieces of hardware that is configured and operated after its initial installation completely remotely. Customers' premises installations are the same architectural concept based on hyperconverged infrastructure and virtualized network functions. The only difference is that as a location is not a data center contracted by the service provider anymore, but the customer's premises, the service provider cannot take responsibility for the availability of services of the customer's facilities, like power, cooling, and physical security. But this is rarely a challenge and just requires a clear demarcation of responsibilities. And enterprises are usually aware that their small on-premise server room does not provide the same availability like an established data center serving hundreds of customers. With this deployment on their premises, enterprises do not get only minimum latencies, but as well independence of any wide area network bandwidth and availability, and control over who has physical access to their data. In case of some compliance regulations, it is more about control than it is about security. For cloud hyperscalers, the evolution has been similar. They are beginning to deploy computing capacity into many edge clouds that are small and provide only a limited set of functionality, typically the basic infrastructure as a service, compute, storage, and networking services. Their purpose is to provide low latencies, and they are not designed to evolve into large hyperscale platforms. Cloud hyperscalers' installations on customers' premise are a special case. as they are not anymore public clouds, but rather private cloud installations. They take standardized hardware, often as well based on hyper-converged infrastructure, and installed their slightly adapted cloud software. Thus, enterprises get the PaaS services and a similar look and feel as they are used to with the public cloud environment, and the low latencies and data access control of an on-premises installation. Another important factor of these environments is a more or less seamless integration with the existing public cloud environments. Examples for such architectures are AWS Outposts, Azure Stack, and Google Kubernetes on-prem. These solutions are in most or nearly in all cases deployed individually. They generate the edge computing benefits of low latencies, bandwidth optimization in the core, and data compliance, but the individuality results as well in a limited geographical reach, one individual installation per location. An example of an edge computing infrastructure that is already installed globally and can be used by many enterprises at the same time is the CenturyLink content delivery network. Over to you, Mark.
Yeah, thanks, Akim. Now we're going to talk through what is edge in the CDN world and what is it in edge compute. So as Akim already told you guys, the edge is like any other edge in a network close to the end user, as you can see here on the edge between access and aggregation. In CDN, we know edge nodes, which is kind of a buzzword, as a caching server, a place where you keep content locally as close to the user as possible. Through this way, you distribute the load throughout, well, the regions or the world, depends on the size of your company. And from there on, you deliver it, reducing latency, making sure your throughput is faster into the local ISPs. And like I said, this phenomenon is called caching. Your browser has cache, your phone has cache, and so does CDN use the exact same caching technology to make sure that your content is replicated throughout the world. Then what is the computing part about CDN edge compute, and how is that different from the others? Well, as you can imagine, like I said, the core in this case is, as Akim said, the core in this case is where the large files, in CDN case, storage for media, storage for large files, are put together. They're being processed, transcoded, and then distributed to the edge locations around the globe. These are, however, very often quite dumb tasks. And what do I mean with dumb tasks? Dumb tasks in such a way that if we're talking about a very small image or maybe a bit of a video, which has to be optimized for the right kind of device, in a lot of cases, the cache server will tell you it is not in cache. I have to go back to the core, which is in this case the center of the network, make sure that the file is cut the right way for the device or optimized in such a way that it works. Then it's being cached again, and the request will be forwarded next time so that the edge server will tell you, all right, it's in cache, I can deliver it. These kind of dumb tasks, so to say, can be done on the edge computed, or on the edge node itself, sorry, without any issues. So what CenturyLink has done, we've partnered up with a technology company called Section.io, and we've implemented their edge computing technology on our vast CDN backbone, which means that whenever it comes to, like I said, cutting an image, making sure the video is the right format, these things will no longer happen centrally, where you reduce the long backhaul and the latency introduced because your client, in fact, has to go all the way to where the content is stored, but it will happen on the edge nodes around the planet. What else is there to edge compute? So in this case, is it just an enhanced edge node or an enhanced caching node? No, there's actually a lot more to it, because there are also security features. There are features to speed up your website. There are possibilities of, for example, optimizing your web shop in certain scripts and load customer Java, HTML, like whatever language you're using, onto our edge CDN edge node, and do the computing locally. So when does it make sense to do this on the edge, and when does it make sense to do it on the core? Well, usually if it is about a small task which can be replicated very fast, which has to do with critical latency performance. Akim gave you the example of a self-driving car. With CDN, we're more looking at a web shop where you want to buy, where your customer wants to buy something. So he clicks on an image, he wants to place a review, or he wants to see the product catalog because he's about to order, let's say, a new computer online. In all these cases, there are very simple tasks. I'm not talking about a database here. No, I'm talking about images. I'm talking about small web scripts, which make this website running smoothly. These are the kind of tasks you want to decentralize over the planet. As close to the end user as possible. But there are also security features. Think about what happens when your website is under or a DDoS attack. You're having malware bots or malicious bots scanning your website, looking for vulnerabilities. These are kind of security measurements which you want to have local in the edge, because these do not happen at the core, and they don't happen on a global scale. It could be, for example, happening in Europe, could be happening in Asia. Then you want this protection locally. You want the acceleration to happen locally. And because of that, we have enhanced our content delivery network with these edge capabilities. On the next slide, I want to show you some of the features. And I say some, I know it is a list, but there are actually 50 of them, 50 plus and growing. These are containerized standards, both open source and proprietary technology, which can be run and enabled on our CDN backbone. Of course, we have Varnish's caching module, but for the more tech guys watching this webinar, you will see tools like Kraken.io, which is a an image optimization service, cutting the image for the right device without going back to the origin, to ThreadX, which is a security application, which can also be run and enabled decentrally, together with Cloudinary, which is a large library to run files local. Signal Science, which I think is also a big name. Like I said, this is just a small list because I think we can put them in 3 breeds of modules. There is the performance type of module, which you want to use for caching, you want to use for image optimization, but also to accelerate your website. This is used to optimize your web shop, reduce latency, and also boost your revenue, because there are many studies out there on the internet proving that every 10 milliseconds corresponds with approximately 1% of revenue. There is the security aspect, which includes a web application firewall, also known as WAF, like I mentioned, bot blocking and DDoS protection. And there is the application side, where you can actually run an application on the edge. Think about A/B testing to check which side corresponds better, or performs better? Is it the A version or the B version? Search engine optimization to make sure that your website is popping up in Google, Bing, and all the large search engines, and many more. When I say many more, are there more given tools? No, it doesn't have to be a given or provided tool. This can also be your code, which is, like I said, a JavaScript or maybe just a piece of HTML, which you want to run on a container-based workload on our platform. I will now hand over back to Akim. We can talk you through the summary. Akim, over to you.
Thanks, Mark. So short summary, what are the key takeaways? First, edge computing is about bringing computing services to, or at least closer to, the place of digital interaction. Second, this does not reduce the need for large-scale data centers and cloud platforms at the core. The cloud is not dead, as proclaimed some years ago provocatively. Third, edge computing reduces the latency between the user and the compute instances. This generally improves the user experience, and sometimes it is even required to enable new services. Thus, edge computing has a direct impact on the business and drives potential opportunities. 4, edge computing increases application performance by moving standardized tasks from the central data center and cloud platforms to the edge. And last but not least, by placing compute functions near the place of digital interaction, edge computing prevents unnecessary backhaul traffic, reducing enterprises' networking costs. Thank you for your attention. In case of any question regarding edge computing and how you could benefit from it, please do not hesitate to contact us.